Good morning, my name is Tristan, and today I'm presenting my ITECH2501 research on the technologies used to build a predictive analytics decision support system. This one is designed to help small Australian e-commerce retailers prevent customer churn before it happens. The two numbers on the right side of the slide tell the story. 26.8% of customers in the dataset jumped, and Australians spent around $82.6 million online last year. The problem is not about lack of customers, it's about a lack of insight into which one are about to leave. Let me quickly frame the business context because the technology choices only make sense if you understand what problem they are solving. Australian retail insolvency rose 31% year-on-year in 2025. Global platforms like Amazon, Temu, Thien are projected to control 36% of Australian e-commerce by the end of this year. And here's the critical number. It costs 5 to 7 times more to acquire new customers than to retain an existing one. The problem isn't that retailers don't have data. Every sale generates a record. The problem is that nothing is reading that data for early warning signs. Retailers discover a customer has churned only after they already left. By that point, winning them back is economically unviable. That gap between data collected and insight acted on is what this decision support system is designed to close. The foundation of any analytics system is its data. I use the online retail customer churn dataset published on CatGo by Eskery in 2024. 1,000 customer records with a churn rate of 26.8%, meaning 268 customers in the dataset are confirmed churned. What makes this dataset particularly useful for this problem is that it's purpose-built for churn analysis. Rather than raw invoice line items, each row represents a single customer with brief label behavioral fields, like how many days since their last purchase, how many transactions they have made, their total spend, their satisfaction score, how many items they returned, and how many support tickets they raised. The table on the right makes a behavioral gap between retained and churn customers immediately visible. Churn customers has not purchased in 164 days on average, compared to 28 days for retained customers. Their satisfaction score were half as high. Their return rates were 5 times higher. These are not subtle signals. They are patterns a model can learn from. Now to the technology. The system runs through 5 stages, and I want to walk you through each one because the technology choices at each stage were deliberate. Stage 1 is data ingestion. Python and the Pandas library load the raw CSV dataset and run the ETL pipeline. Missing values are handled, rises are converted from USD to AUD, and the clean data is structured for analysis. Stage 2 is feature engineering. 6 behavioral features are extracted for each customer, including days in last purchase, number of purchases, total spend, satisfaction score, number of returns, and number of support tickets raised. These 6 variables represent the recency, frequency, monetary, and the service quality dimensions of customer behavior, which is the richer signal than traditional RFM analysis alone. Stage 3 is the random forest classifier, the predictive core. I will go deeper on this on the next slide, but for now, the key output I want to say is the churn probability score between 0 and 1 for every customer. In stage 4, the Power PI dashboard. This is business performance management layer, surfacing which customers are flagged, what their risk score is, and how much annual revenue is at stake if they leave. This turns model output into something a business owner can look at and act on. Stage 5 is automatic intervention, the restricted layer. When a customer's churn score crosses the threshold, The system automatically selects and triggers an appropriate retention action. That might be an email through MailChimp API or a flag in the CRM for personal call. The classification algorithm is the heart of this system, and I want to explain why random forest was chosen over the other techniques in this unit. A single decision tree is intuitive but prone to overfitting. It memorizes the training data rather than learning the patterns that generalize to new customers. Random forest corrects this by building 100 decision tree, each trained on a random subset of data and a random subset of features. The final churn prediction for each customer is determined by majority vote across all 100 trees. That acceleration is what makes it stable. I also consider neural networks, but the unit identified their key weaknesses, that is, the black box problems. Neural networks can be highly accurate, but their internal logic is adequate. A retailer who gets a flag saying this customer is at risk needs to understand why, so they can grab the right message. Random forest solve this with future importance scorers, which show exactly which input variables drove the reduction. Look at the chart in the right. Days since last purchase accounts for 47% of predictive weight, satisfaction score accounts for 22%. Together, those two factors explain nearly 70% of what tried junk. That's the message a business can act on to re-engage the customers who have been quiet for a while and prioritize those who have a poor experience. On the performance side, 84.5% accuracy, AUC ORC of 0.891. That means the model is strongly discriminating between the customers who will jump and those who won't, well above the 50% baseline of random guessing. Knowing that the customers will probably jump is only half the solution. The restricted layer is what converts the probability into a business decision. The rule is straightforward. If a customer churn probability exceeds 0.7, the system selects an intervention based on their value target. Like high-value customers, who spend over $3,000, receive a personalized 15% discount code and a CRM flag for direct outreach. Mid-value customers get an automated reinstatement email with the product recommendations based on their purchase history. Low-value customers receive a loyalty points bonus notification. The logic here is that the intervention cost should be proportional to expected return. You don't spend $20 reaching out personally to a customer who spend $50 total, and you don't just send a loyalty email to someone who spent $5,000. The business impact on the right panel tells you what this means at scale. 268 at-risk customers identified, a targeted reinvestment rate of 18 to 25% compared to 5 to 8% for general broadcast. Projected revenue recovery of $41,000 annually, a return of 7 to 14 times the implementation cost of the system. To close, 4 things I want you to take away from this presentation. First, Python and Pandas handle the ETL pipeline, transform raw customer records into the clean predictive behavioral signals that the model can learn from. Second, random forest scores every customer churn probability with 84.5% accuracy and an AUC ROC of 0.891, and it does transparently without the black box problem of neural networks. Third, Power BI surfaced the risk scores and revenue at risk for the business owners, turning a model output into a decision that they can actually act on. And fourth, the restricted layer automates the right intervention for the right customers, calibrated by value target, not a generic broadcast. It's a targeted action triggers at the moment it's needed. So the goal of the system isn't just about predict the future. It's also about to give small Australian retailers enough advance warning to change it. Thank you.